All right, so in the last video, what we did is we started with the equation and we came up with the eccentricity and the distance to the directrix. And we could have just as easily gave the actual equation of the directrix if we would have liked to. So now what we're going to do is we're going to do a few examples where we reverse that, where we give you the eccentricity and the directrix, and we're going to find the polar equation for the conic. And obviously all of these conics are going to have focus at the pole, or at least a focus is going to be at the pole. So let's go into an example here. So we're going to have a parabola with obviously all parabolas have to have eccentricity of 1 and a directrix, which is x equal -3. And I want to come up with the equation for that parabola. Again, this parabola will have its focus at the pole. So what we do, whoops, is we start out with a graph and simply look at the x equals -3. X equals -3 is a vertical line here. So that tells me what this parabola is going to be doing. Namely, that the parabola is going to come about -1.5, somewhere in there is going to be their vertex, and it's going to be pointed out. So it's going to sweep, obviously a lot smoother than what I'm drawing, but it's going to sweep out like that. In other words, it's going to be pointed right. Now, what that means for us is that the equation that we're going to have to use is going to have to be the one dealing with cosine. Let me explain what I mean by that. So we have this parabola whose eccentricity is 1, directrix is x equals -3. I want to choose either this equation or this form of an equation for my conic section. Now, because we're pointed left and right, we're going to use the conic section that deals with the cosine. You can play around with that if you like. If you forget which one points left and right and which one points up and down, go ahead and, just type a couple of things on your calculator and figure it out. But you can trust me that cosine is going to be the one pointed left and right. Now we have eccentricity of 1, so we know we can fill in the e's with a 1, and we have to choose whether you use a plus or a minus here. I am always going to use the plus, and I'll show you why I always do that. So what happens is I get something like this. I get r equals the eccentricity times d. Now the d here is the distance between my pole, again 0, and the directrix x equals -3. I'm going to choose that d to be -3 because we have x equals -3 here, and I'm going to do a plus 1 in the denominator. So in other words, the reason I chose to use the plus sign in the denominator was so that I can just use this number -3 directly as my value for d. So the d value is -3. It's exactly what this number is. If it's x equals a number, whatever that number happens to be, I can just plug it in for d as long as I use the plus on the denominator. Hopefully that all makes sense. So I get r is equal to 1 times -3 over 1 plus 1 cosine theta. And what I would do there is just simplify 1 times -3 is simply -3. And there it is. That's done. That is the parabola. That is the polar equation for the parabola whose focus is at the pole and who has eccentricity of 1, directrix at x equals -3. You can confirm that if you want to graph. Obviously, use your calculator to do this, use some other software if you'd like. I'll show you the graph that I came up with. I came up with this graph right here. So when you plug in r equals -3 over 1 plus 1 cosine theta, you get the exact thing I was looking for there. All right. By the way, if you didn't, if all of a sudden you put in the wrong value, if you did instead of a plus, if you did a minus, then it's going to be pointed the wrong way, and you're going to see that clearly when you graph. So it's always a good practice to check your work and see that you actually did get the right graph, the graph that you were looking for. So let's do another one. I want you to try this on your own. Find the equation for this conic with a focus at the pole, with one of its foci, I should say, at the pole, a focus at the pole. Hopefully you went ahead and did that. Now, my equation here of the directrix is y equals 1. Notice what that's going to do. That y equals 1 is a horizontal line, so that's going to force me to have this ellipse sort of stretched out further up and down than it is left and right. So our focus here at the origin or at the pole, we're going to be stretched out um, up and down more. So what that tells me is that when I'm creating this equation, I need to choose the sine theta version. So I need to take r equals ed over 1 plus or minus e sine theta. Now, like I said, e is 3/4. So we just plug that into our denominator. And by the way, I always use a plus there. And so I got 1 plus 3/4 sine theta. The d here, well, since y is equal to 1, the distance from the origin or the pole to y equals 1 is simply 1. So we get r equals 3/4 times 1 over 1 plus 3/4 sine theta. 3/4 times 1 is just 1. So if you'd like to simplify that to 3/4 over 1 plus 3/4 sine theta, you can. And that is the equation of the ellipse you want. You can confirm that by graphing. Let me show you my graph of that. My graph looks like this. So you can see that we do get the right type of graph. And here's our directrix once again at 1, and you can see what's happening here. So that's the idea. So let's do another version of that. I would like you to do example 8 here. So we have another ellipse, eccentricity of 1/5, directrix at x equals -2. Push pause on the video and do that on your own. First thing is to notice that x equals -2 is a vertical line. And so our ellipse is going to be stretched out left and right more than it's stretched out up and down. So we're going to use the cosine version of the equation. So we're going to use r equals ed over 1 plus or minus e cosine theta. I'll always obviously use the plus. So we get r equals 1/5. The d is the distance from directrix to the pole, so d is -2. So 1/5 times -2 over 1 plus 1/5 cosine theta. And if you want to simplify that numerator, you can write that as -2/5 because -1/5, or excuse me, 1/5 times -2 is -2/5. So if you'd like to simplify that way, that's fine. Also, some people like to get rid of the fractions by multiplying top and bottom by 5. I tend to not do that because I think it's a little bit easier. It's just another step that I really don't need to do. So I think it's easier just to leave it as is. So there you go. I won't graph this one, but that's the um, polar equation that you should get. Let's do one more. Let's take a hyperbola with eccentricity of 2, whose directrix is at x equals 1. Go ahead and push pause on the video and do that. So if you graph x equals 1, you get a vertical line again. I want you to just note that the hyperbola is going to be pointing sort of left and pointing right. And that means that I'm going to have to use cosine, the cosine version of the equation. So I'm going to use the r equals ed over 1 plus or minus e cosine theta version. Now again, e is 2, we just plug in 2 for that. So 1 plus 2 cosine theta in the denominator. In the numerator, e is 2. The distance from the pole to the directrix is 1, so 2 times 1. If you want to simplify that, 2 times 1 is just 2. So there you go. That is the polar form of the equation that I'm looking for. And you can go ahead and graph that if you would like. R equals 2 over 1 plus 2 times cosine theta. Okay, and you can see how the hyperbola is here. And also, notice again, vertical line, we want to be pointing left and right so that we don't cross that vertical line. Okay, and you can see fairly clearly that your focus, one of your foci, I should say, is at the pole, or in other words, the origin. So there you go. That is how we create those polar equations when we know the eccentricity, when we know the directrix. By the way, notice that on all of these previous ones, the directrix, when we had x equals something, we were pointing left and right, so we were using cosine version. When my directrix was y equals something, we were pointing up and down, so we used the sine version. All right, so that's that. If you'd like to try example 10 on your own, you can go ahead and do that, another hyperbola with eccentricity of 3.5, directrix y equals 3. You can push pause on the video now. I'll give you the solution in just a moment. All right, there it is. So hopefully you got this. We had directrix y equals something, so we're going to use the sine version. E is 3.5, D is 3. So 3.5 times 3 in the numerator. In the denominator, 1 plus 3.5 times sine theta. Again, directrix is y equals, and that's how we do that. By the way, 3.5, when you take 3.5, multiply it times 3, you get 10.5. So if we're a little bit sticklers about that, we usually always simplify the numerators. So 10.5 over 1 plus 3.5 times sine theta is the answer there. Now, the last part of the 10.6 has to do with Kepler's laws. I'll address those in the next video.